The General Dynamics F-16 Fighting Falcon is a single-engine supersonic multi-role fighter aircraft originally developed by General Dynamics, now Lockheed Martin, for the United States Air Force, U.S. Air Force. Designed as an air superiority day fighter, it evolved into a successful all-weather multi-role aircraft. Over 4,500 aircraft have been built since production was approved in 1976. Although no longer being purchased by the U.S. Air Force, improved versions are being built for export customers. In 1993, General Dynamics sold its aircraft manufacturing business to the Lockheed Corporation, which in turn became part of Lockheed Martin after a 1995 merger with Martin Marietta. The Fighting Falcon's key features include a frameless bubble canopy for better visibility, side-mounted control stick to ease control while maneuvering, a seat reclined 30 degrees to reduce the effect of G-forces on the pilot, and the first use of a relaxed static stability / fly-by-wire flight control system which helps to make it a nimble aircraft. The F-16 has an internal M61 Vulcan cannon and 11 locations for mounting weapons and other mission equipment. The F-16's official name is Fighting Falcon, but Viper is commonly used by its pilots and crews, due to a perceived resemblance to a Viper snake as well as the colonial Viper starfighter on Battlestar Galactica. In addition to active duty for U.S. Air Force Reserve Command, and Air National Guard units, the aircraft is also used by the U.S. Air Force Aerial Demonstration Team, the U.S. Air Force Thunderbirds, and as an adversary/aggressor aircraft by the United States Navy. The F-16 has also been procured to serve in the air forces of 25 other nations. As of 2015, it is the world's most numerous fixed-wing aircraft in military service. Development. Lightweight fighter program. Experiences in the Vietnam War revealed the need for air superiority fighters and better air-to-air training for fighter pilots. Based on his experiences in the Korean War and as a fighter tactics instructor in the early 1960s, Colonel John Boyd with mathematician Thomas Christie developed the energy maneuverability theory to model a fighter aircraft's performance in combat. Boyd's work called for a small, lightweight aircraft that could maneuver with the minimum possible energy loss, and which also incorporated an increased thrust-to-weight ratio. In the late 1960s, Boyd gathered a group of like-minded innovators who became known as the Fighter Mafia, and in 1969, they secured Department of Defense funding for General Dynamics and Northrop to study design concepts based on the theory. Air Force FX proponents remained hostile to the concept because they perceived it as a threat to the F-15 program. However, the Air Force's leadership understood that its budget would not allow it to purchase enough F-15 aircraft to satisfy all of its missions. The Advanced Day Fighter concept, renamed FXX, gained civilian political support under the reform-minded Deputy Secretary of Defense David Packard, who favored the idea of competitive prototyping. As a result, in May 1971, the Air Force Prototype Study Group was established, with Boyd a key member, and 2 of its 6 proposals would be funded, one being the Lightweight Fighter, LWF. The request for proposals issued on January 6, 1972 called for a 20,000 pound, 9,100 kilograms, class air-to-air day fighter with a good turn rate, acceleration, and range, and optimized for combat at speeds of Mach 0.6 and altitudes of 30,000 40,000 feet, 9,112,000 m. This was the region where U.S. Air Force studies predicted most future air combat would occur. The anticipated average flyaway cost of a production version was $3 million. This production plan, though, was only notional, as the U.S. Air Force had no firm plans to procure the winner. Finalists selected and flyoff. 5 companies responded, and in 1972, the Air Staff selected General Dynamics Model 401 and Northrop's P600 for the follow-on prototype development and testing phase. GD and Northrop were awarded contracts worth $37.9 million and $39.8 million to produce the YF-16 and YF-17, respectively, with first flights of both prototypes planned for early 1974. To overcome resistance in the Air Force hierarchy, the fighter mafia and other LWF proponents successfully advocated the idea of complementary fighters in a high-cost/low-cost force mix. The high/low mix would allow the U.S. Air Force to be able to afford sufficient fighters for its overall fighter force structure requirements. The mix gained broad acceptance by the time of the prototype's flyoff, defining the relationship of the LWF and the F-15. The YF-16 was developed by a team of General Dynamics engineers led by Robert H. Widmer. The first YF-16 was rolled out on December 13, 1973, and its 90-minute maiden flight was made at the Air Force Flight Test Center, AFTC, at Edwards AFB, California, on February 2, 1974. Its actual first flight occurred accidentally during a high-speed taxi test on January 20, 1974. While gathering speed, a roll control oscillation caused a fin of the portside wingtip-mounted missile and then the starboard stabilator to scrape the ground, and the aircraft then began to veer off the runway. The test pilot, Phil Oestricher, decided to lift off to avoid a potential crash, safely landing 6 minutes later. The slight damage was quickly repaired and the official first flight occurred on time. The YF-16's first supersonic flight was accomplished on February 5, 1974, and the second YF-16 prototype first flew on May 9, 1974. This was followed by the first flights of Northrop's YF-17 prototypes on June 9 and August 21, 1974, respectively. During the flyoff, the YF-16's completed 330 sorties for a total of 417 flight hours. The YF-17's flew 288 sorties, covering 345 hours. Air Combat Fighter Competition. Increased interest turned the LWF into a serious acquisition program. North Atlantic Treaty Organization, NATO, allies Belgium, Denmark, the Netherlands, and Norway were seeking to replace their F-104G Starfighter fighter bombers. In early 1974, they reached an agreement with the U.S. that if the U.S. Air Force ordered the LWF winner, they would consider ordering it as well. The U.S. Air Force also needed to replace its F-105 Thunder Chief and F-4 Phantom II fighter bombers. The U.S. Congress sought greater commonality in fighter procurements by the Air Force and Navy, and in August 1974 redirected Navy funds to a new Navy Air Combat Fighter, NACF, program that would be a navalized fighter-bomber variant of the LWF. The four NATO allies had formed the Multinational Fighter Program Group, MFPG, and pressed for a U.S. decision by December 1974, thus, the U.S. Air Force accelerated testing. To reflect this serious intent to procure a new fighter bomber, the LWF program was rolled into a new Air Combat Fighter, ACF, competition in an announcement by U.S. Secretary of Defense James R. Schlesinger in April 1974. The ACF would not be a pure fighter, but multi-role, and Schlesinger made it clear that any ACF order would be in addition to the F-15, which extinguished opposition to the LWF. ACF also raised the stakes for GD and Northrop because it brought in competitors intent on securing what was touted at the time as the arms deal of the century. These were Dassault Breguet's proposed Mirage F-1M53, the Anglo-French Seppicat Jaguar, and the proposed Saab 370 Eurofighter. Northrop offered the P-530 Cobra, which was similar to the YF-17. The Jaguar and Cobra were dropped by the MFPG early on, leaving two European and the two U.S. candidates. On September 11, 1974, the U.S. Air Force confirmed plans to order the winning ACF designed to equip 5 tactical fighter wings. Though computer modeling predicted a close contest, the YF-16 proved significantly quicker going from one maneuver to the next, and was the unanimous choice of those pilots that flew both aircraft. On January 13, 1975, Secretary of the Air Force John L. McLucas announced the YF-16 as the winner of the ACF competition. The chief reasons given by the Secretary were the YF-16's lower operating costs, greater range, and maneuver performance that was significantly better than that of the YF-17, especially at supersonic speeds. Another advantage of the YF-16 unlike the YF-17 was its use of the Pratt & Whitney F100 turbofan engine, the same power plant used by the F-15. Such commonality would lower the cost of engines for both programs. Secretary McLucas announced that the U.S. Air Force planned to order at least 650, possibly up to 1,400 production F-16s. In the Navy Air Combat Fighter, NACF, competition, on May 2, 1975 the Navy selected the YF-17 as the basis for what would become the McDonnell Douglas F/A-18 Hornet. Into production. The U.S. Air Force initially ordered 15 full-scale development, FSD, aircraft, 11 single-seat and 4 two-seat models, for its flight test program, but was reduced to 8, 6 F-16A single-seaters and 2 F-16B two-seaters. The YF-16 design was altered for the production F-16. The fuselage was lengthened by 10.6 in, 0.269 m, a larger nose radome was fitted for the IN/APG-66 radar, wing area was increased from 280 sq fort, 26 square meters, to 300 sq fort, 28 square meters, the tail fin height was decreased, the ventral fins were enlarged, 2 more stores stations were added, and a single door replaced the original nosewheel double doors. The F-16's weight was increased by 25% over the YF-16 by these modifications. The FSD F-16s were manufactured by General Dynamics in Texas at United States Air Force Plant 4 in late 1975. The first F-16A rolled out on October 20, 1976 and first flew on December 8. The initial two-seat model achieved its first flight on August 8, 1977. The initial production standard F-16A flew for the first time on August 7, 1978 and its delivery was accepted by the U.S. Air Force on January 6, 1979. The F-16 was given its formal nickname of Fighting Falcon on July 21, 1980, entering U.S. Air Force operational service with the 34th Tactical Fighter Squadron, 388th Tactical Fighter Wing at Hill AFB in Utah on October 1, 1980. On June 7, 1975, the 4 European partners, now known as the European Participation Group, signed up for 348 aircraft at the Paris Air Show. This was split among the European Participation Air Forces, EPAF, as 116 for Belgium, 58 for Denmark, 102 for the Netherlands, and 72 for Norway. 2 European production lines, one in the Netherlands at Fokker's Schiphol-Oost facility and the other at Sabca's Gosselies plant in Belgium, would produce 184 and 164 units respectively. Norway's Kongsberg Våpenfabrik and Denmark's Terma A/S also manufactured parts and sub-assemblies for EPAF aircraft. European CO production was officially launched on July 1, 1977 at the Fokker factory. Beginning in November 1977, Fokker-produced components were sent to Fort Worth for fuselage assembly, then shipped back to Europe for final assembly of EPAF aircraft at the Belgian plant on February 15, 1978. Deliveries to the Belgian Air Force began in January 1979. The first Royal Netherlands Air Force aircraft was delivered in June 1979. In 1980, the first aircraft were delivered to the Royal Norwegian Air Force by Sabca and to the Royal Danish Air Force by Fokker. During the late 1980s and 1990s, Turkish Aerospace Industries, TAI, produced 232 Block 30/40/50 F-16s on a production line in Ankara under license for the Turkish Air Force. TAI also produced 46 Block 40s for Egypt in the mid-1990s and 30 Block 50 from 2010. Korean Aerospace Industries opened a production line for the KF-16 program, producing 140 Block 52s from the mid-1990s to mid-2000s decade. If India had selected the F-16 in for its medium multi-role combat aircraft procurement, a 6th F-16 production line would have been built in India. In May 2013, Lockheed Martin stated there were currently enough orders to keep producing the F-16 until 2017. Improvements and upgrades. One change made during production was augmented pitch control to avoid deep stall conditions at high angles of attack. The stall issue had been raised during development, but had originally been discounted. Model tests of the YF-16 conducted by the Langley Research Center revealed a potential problem, but no other laboratory was able to duplicate it. YF-16 flight tests were not sufficient to expose the issue. Later flight testing on the FSD aircraft demonstrated there was a real concern. In response, the areas of the horizontal stabilizer were increased 25% on the Block 15 aircraft in 1981 and later retrofitted to earlier aircraft. In addition, a manual override switch to disable the horizontal stabilizer flight limiter was prominently placed on the control console, allowing the pilot to regain control of the horizontal stabilizers, which the flight limiters otherwise lock in place, and recover. Besides reducing the risk of deep stalls, the larger horizontal tail also improved stability and permitted faster takeoff rotation. In the 1980s, the Multinational Staged Improvement Program, MSIP, was conducted to evolve the F-16's capabilities, mitigate risks during technology development, and ensure the aircraft's worth. The program upgraded the F-16 in 3 stages. The MSIP process permitted the quick introduction of new capabilities, at lower costs and with reduced risks compared to traditional independent upgrade programs. In 2012, the U.S. Air Force had allocated $2.8 billion to upgrade 350 F-16s while waiting for the F-35 to enter service. One key upgrade has been an auto-GCAS, ground collision avoidance system, to reduce instances of controlled flight into terrain. Onboard power and cooling capacities limits the scope of upgrades, which often involves the addition of more power-hungry avionics. Lockheed won many contracts to upgrade foreign operators' F-16s. B Systems also offers various F-16 upgrades, receiving orders from South Korea, Oman, Turkey, and the U.S. Air National Guard. B lost the South Korean contract due to a price breach in November 2014. In 2012, the U.S. Air Force assigned the total upgrade contract to Lockheed Martin. Upgrades include Raytheon's Center Display Unit, which replaces several analog flight instruments with a single digital display. In 2013, sequestration budget cuts cast doubt on the U.S. Air Force's ability to complete the Combat Avionics Programmed Extension Suite, CAPES, a part of secondary programs such as Taiwan's F-16 upgrade. ACC's General Mike Hostage stated that if he only had money for SLEP, Service Life Extension Program, or CAPES, he would fund SLEP to keep the aircraft flying. Lockheed Martin responded to talk of CAPES cancellation with a fixed-price upgrade package for foreign users. CAPES was not included in the Pentagon's 2015 budget request. The U.S. Air Force said that the upgrade package will still be offered to the Republic of China Air Force, and Lockheed said that some common elements with the F-35 will keep the radar's unit costs down. In 2014, the U.S. Air Force issued a RFI to SLEP 300 F-16C/DS. Moving production line. After building F-16 fighter jets for more than 4 decades in Texas, Lockheed Martin plans to move the production line to South Carolina, where it will build new versions of the venerable combat aircraft for U.S. allies. Lockheed will deliver the last F-16 from its Fort Worth factory in September 2017, then take a 2-year break in production to move the line to Greenville, South Carolina, the head of the firm's aeronautics sector said Tuesday. Dwindling orders make the break possible. While engineering, design, and modernization activities will remain in Fort Worth, the last Cowtown jet flew out of town November 14, 2017. Design Overview. The F-16 is a single-engine, highly maneuverable, supersonic, multi-role tactical fighter aircraft. It was designed to be a cost-effective combat workhorse that can perform various missions and maintain around-the-clock readiness. It is much smaller and lighter than predecessors, but uses advanced aerodynamics and avionics, including the first use of a relaxed static stability/fly-by-wire (RSS/FBW) flight control system, to achieve enhanced maneuver performance. Highly nimble, the F-16 was the first fighter aircraft purpose-built to pull 9G maneuvers and can reach a maximum speed of over Mach 2. Innovations include a frameless bubble canopy for better visibility, side-mounted control stick, and reclined seat to reduce G-force effects on the pilot. It is armed with an internal M61 Vulcan cannon in the left wing root and has multiple locations for mounting various missiles, bombs, and pods. It has a thrust-to-weight ratio greater than 1, providing power to climb and accelerate vertically. The F-16 was designed to be relatively inexpensive to build and simpler to maintain than earlier generation fighters. The airframe is built with about 80% aviation-grade aluminum alloys, 8% steel, 3% composites, and 1.5% titanium. The leading-edge flaps, stabilators, and ventral fins make use of bonded aluminum honeycomb structures and graphite epoxy lamination coatings. The number of lubrication points, fuel line connections, and replaceable modules is significantly lower than predecessors. 80% of access panels can be accessed without stands. The air intake was placed so it was rearward of the nose but forward enough to minimize airflow losses and reduce aerodynamic drag. Although the LWF program called for a structural life of 4,000 flight hours, capable of achieving 7.33 grams with 80% internal fuel, GD's engineers decided to design the F-16's airframe life for 8,000 hours and for 9G maneuvers on full internal fuel. This proved advantageous when the aircraft's mission changed from solely air-to-air combat to multi-role operations. Changes in operational use and additional systems have increased weight, necessitating multiple structural strengthening programs. General configuration. The F-16 has a cropped delta wing incorporating wing fuselage blending and 4 body vortex control strakes, a fixed geometry, underslung air intake, with splitter plate, to the single turbofan jet engine, a conventional triplane empennage arrangement with all moving horizontal stabilator tailplanes, a pair of ventral fins beneath the fuselage aft of the wing's trailing edge, and a tricycle landing gear configuration with the aft retracting, steerable nose gear deploying a short distance. Behind the inlet lip, there is a boom-style aerial refueling receptacle located behind the single-piece bubble canopy of the cockpit. Split-flap speed brakes are located at the aft end of the wing body fairing, and a tail hook is mounted underneath the fuselage. A fairing beneath the rudder often houses ECM equipment or a drag chute. Later F-16 models feature a long dorsal fairing along the fuselage's spine, housing additional equipment or fuel. Aerodynamic studies in the 1960s demonstrated that the vortex lift phenomenon could be harnessed by highly swept wing configurations to reach higher angles of attack, using leading-edge vortex flow off a slender lifting surface. As the F-16 was being optimized for high combat agility, GD's designers chose a slender cropped delta wing with a leading-edge sweep of 40 degrees and a straight trailing edge. To improve maneuverability, a variable camber wing with the NACA 64A204 airfoil was selected. The camber is adjusted by leading edge and trailing edge flap airons linked to a digital flight control system, FCS, regulating the flight envelope. The F-16 has a moderate wing loading, reduced by fuselage lift. The vortex lift effect is increased by leading edge extensions, known as strakes. Strakes act as additional short span, triangular wings running from the wing root, the juncture with the fuselage, to a point further forward on the fuselage. Blended into the fuselage and along the wing root, the strake generates a high-speed vortex that remains attached to the top of the wing as the angle of attack increases, generating additional lift and allowing greater angles of attack without stalling. Strakes allow a smaller, lower aspect ratio wing, which increases roll rates and directional stability while decreasing weight. Deeper wing roots also increase structural strength and internal fuel volume. Armament. Early F-16s could be armed with up to 6 AIM-9 Sidewinder heat-seeking short-range air-to-air missiles, AAM, by employing rail launchers on each wingtip, as well as radar-guided AIM-7 Sparrow medium-range AAMs in a weapons mix. More recent versions support the AIM-120 AMRAAM. The aircraft can carry various other AAMs, a wide variety of air-to-ground missiles, rockets, or bombs, electronic countermeasures, ECM, navigation, targeting or weapons pods, and fuel tanks on 9 hardpoints, 6 under the wings, 2 on wingtips, and 1 under the fuselage. 2 other locations under the fuselage are available for sensor or radar pods. The F-16 carries a 20 mm, 0.787 in, M61A1 Vulcan cannon for close-range aerial combat and strafing. The 20 mm cannon is mounted inside the fuselage to the left of the cockpit. Negative stability and fly-by-wire. The F-16 was the first production fighter aircraft intentionally designed to be slightly aerodynamically unstable, also known as relaxed static stability, RSS, to improve maneuverability. Most aircraft are designed with positive static stability, which induces aircraft to return to straight and level flight attitude if the pilot releases the controls. This reduces maneuverability as the inherent stability has to be overcome. Aircraft with negative stability are designed to deviate from controlled flight and thus be more maneuverable. At supersonic speeds, the F-16 gains stability, eventually positive, due to aerodynamic changes. To counter the tendency to depart from controlled flight and avoid the need for constant trim inputs by the pilot, the F-16 has a quadruplex, 4-channel, fly-by-wire, FBW, flight control system, FLCS. The Flight Control Computer, FLCC, accepts pilot input from the stick and rudder controls, and manipulates the control surfaces in such a way as to produce the desired result without inducing control loss. The FLCC conducts thousands of measurements per second on the aircraft's flight attitude to automatically counter deviations from the pilot set flight path, leading to a common aphorism among pilots: "You don't fly an F-16, it flies you." The FLCC further incorporates limiters governing movement in the 3 main axes based on attitude, airspeed, and angle of attack, AOA. These prevent control surfaces from inducing instability such as slips or skids, or a high AOA inducing a stall. The limiters also prevent maneuvers that would exert more than a 9 grams load. Flight testing has revealed that assaulting multiple limiters at high AOA and low speed can result in an AOA far exceeding the 25 degrees limit, colloquially referred to as departing. This causes a deep stall, a near free fall at 50 degrees to 60 degrees AOA, either upright or inverted. While at a very high AOA, the aircraft's attitude is stable but control surfaces are ineffective. The pitch limiter locks the stabilators at an extreme pitch up or pitch down attempting to recover. This can be overridden so the pilot can rock the nose via pitch control to recover. Unlike the YF-17, which had hydromechanical controls serving as a backup to the FBW, General Dynamics took the innovative step of eliminating mechanical linkages between the control stick and rudder pedals, and the flight control surfaces. The F-16 is entirely reliant on its electrical systems to relay flight commands, instead of traditional mechanically linked controls, leading to the early moniker of the electric jet. The quadruplex design permits graceful degradation in flight control response in that the loss of one channel renders the FLCS a triplex system. The FLCC began as an analog system on the A/B variants, but has been supplanted by a digital computer system beginning with the F-16C/D Block 40. The F-16S controls suffered from a sensitivity to static electricity or electrostatic discharge, ESD. Up to 70–80% of the C/D model's electronics were vulnerable to ESD. Cockpit and ergonomics. A key feature of the F-16S cockpit is the exceptional field of view. The single-piece, bird-proof polycarbonate bubble canopy provides 360 degrees all-round visibility, with a 40 degrees look-down angle over the side of the aircraft, and 15 degrees down over the nose. Compared to the common 12–13 degree of preceding aircraft, the pilot's seat is elevated for this purpose. Furthermore, the F-16S canopy lacks the forward bow frame found on many fighters, which is an obstruction to a pilot's forward vision. The F-16S ACES 20/0 ejection seat is reclined at an unusual tilt-back angle of 30 degrees. Most fighters have a tilted seat at 13–15 degree. The tilted seat can accommodate taller pilots and increases G-force tolerance, however it has been associated with reports of neck ache, possibly caused by incorrect headrest usage. Subsequent U.S. fighters have adopted more modest tilt-back angles of 20 degrees. Due to the seat angle and the canopy's thickness, the ejection seat lacks canopy breakers for emergency egress. Instead, the entire canopy is jettisoned prior to the seat's rocket firing. The pilot flies primarily by means of an armrest-mounted side stick controller, instead of a traditional center-mounted stick, and an engine throttle. Conventional rudder pedals are also employed. To enhance the pilot's degree of control of the aircraft during high-G combat maneuvers, various switches and function controls were moved to centralized hands-on throttle and stick (HOTAs) controls upon both the controllers and the throttle. Hand pressure on the side stick controller is transmitted by electrical signals via the FBW system to adjust various flight control surfaces to maneuver the F-16. Originally, the side stick controller was non-moving, but this proved uncomfortable and difficult for pilots to adjust to, sometimes resulting in a tendency to over-rotate during takeoffs, so the control stick was given a small amount of play. Since introduction on the F-16, HOTAS controls have become a standard feature on modern fighters. The F-16 has a head-up display, HUD, which projects visual flight and combat information in front of the pilot without obstructing the view. Being able to keep his head out of the cockpit improves a pilot's situation awareness. Further flight and systems information are displayed on multifunction displays, MFD. The left-hand MFD is the primary flight display, PFD, typically showing radar and moving maps. The right-hand MFD is the system display, SD, presenting information about the engine, landing gear, slat and flap settings, and fuel and weapons status. Initially, the F-16A/B had monochrome cathode ray tube, CRT, displays, replaced by color liquid crystal displays on the block 50/50 seconds. The MLU introduced compatibility with night vision goggles, NVG. The Boeing Joint Helmet Mounted Cueing System, JHMCS, is available from block 40 onwards, for targeting based on where the pilot's head faces, unrestricted by the HUD, using high off-boresight missiles like the AIM-9X. Fire Control Radar. The F-16A/B was originally equipped with the Westinghouse/APG-66 Fire Control Radar. Its slotted planar array antenna was designed to be compact to fit into the F-16's relatively small nose. In a PLUC mode, the APG-66 uses a low pulse repetition frequency, PRF, for medium and high altitude target detection in a low clutter environment, and in look-down/shoot-down employs a medium PRF for heavy clutter environments. It has 4 operating frequencies within the X-band, and provides 4 air-to-air and 7 air-to-ground operating modes for combat, even at night or in bad weather. The Block 15's APG-66 V2 model added a more powerful signal processing, higher output power, improved reliability, and increased range in cluttered or jamming environments. The Midlife Update (MLU) program introduced a new model, APG-66 V2A, which features higher speed and more memory. The AN/APG-68, an evolution of the APG-66, was introduced with the F-16C/D Block 25. The APG-68 has greater range and resolution, as well as 25 operating modes, including ground mapping, Doppler beam sharpening, ground moving target indication, C-target, and track while scan, TWS, for up to 10 targets. The Block 40/42 APG-68 V1 model added full compatibility with Lockheed Martin low-altitude navigation and targeting infrared for night, lantern, pods, and a high PRF pulse Doppler track mode to provide continuous wave radar, CW, target illumination for semi-active radar homing, SARH, missiles like the AIM-7 Sparrow. Block 50/50 seconds F-16S initially used the more reliable APG-68 V5, which has a programmable signal processor employing very high-speed integrated circuit VSIC technology. The advanced Block 50/50 seconds, or 50+/52+, are equipped with the APG-68 V9 radar, with a 30% greater air-to-air detection range and a synthetic aperture radar (SAR) mode for high-resolution mapping and target detection recognition. In August 2004, Northrop Grumman were contracted to upgrade the APG-68 radars of Block 40/42/50/52 aircraft to the V-10 standard, providing all-weather autonomous detection and targeting for Global Positioning System, GPS, aided precision weapons, SAR mapping and terrain-following radar, TF, modes, as well as interleaving of all modes. The F-16E/F is outfitted with Northrop Grumman's AN/APG-80 Active Electronically Scanned Array, AESA, radar. Northrop Grumman developed the latest AESA radar upgrade for the F-16, selected for U.S. Air Force and Republic of China Air Force F-16 upgrades, named the Scalable Agile Beam Radar, SABR. In July 2007, Raytheon announced that it was developing a next-generation radar, Wrangler, based on its earlier AN/APG-79 AESA radar as a competitor to Northrop Grumman's AN/APG-68 and AN/APG-80 for the F-16. Propulsion.
Please subscribe and thanks for watching.